All right, chemistry, this is part 3 of the answers video. We're now moving on to a second type of empirical formula problem. This is the one where we compute the empirical formula from a combustion reaction. Okay, so the first thing we have to do is we are given grams. This is what we came out with in the lab. We have to convert that into moles of carbon dioxide and then ultimately into moles of carbon. That's what we're interested in, is a carbon. Here it's moles of H2O and ultimately into moles of hydrogen. So I'm going to go ahead and do those silently and you follow along, compute the molar mass. Okay, so we'll come down here and do that. So we're going to start with the carbon dioxide and you write a 2 conversion equation. Okay, so right here we have 26.4 grams. It's in the grams row right here. And over here we have 14.4 grams of H2O. So we use the molar mass of carbon dioxide to get to the moles of carbon dioxide, but we don't actually do that calculation. We then use the moles of carbon for every mole of CO2. So if you look at this, if I put a 1 right here and a 1 right there, there's 1 mole of carbon for every 1 mole of CO2. Right? So we'll go ahead and write out that equation. Grams of carbon dioxide, moles of carbon dioxide, moles of carbon dioxide, and the last man standing is moles of carbon. Okay, and that gives us 0.6 moles of carbon. Okay, now we come down and do the same thing for H2O. Okay, for water, you have 2 moles of hydrogen for every 1 mole of water. So 2 moles of hydrogen for every 1 mole of water. You need 2 wheels to make 1 bicycle and 2 hydrogen to make 1 molecule of water. Okay, so grams, moles, and you end up with moles of H. Okay, and for that you will end up with 1.6 moles of H. Okay, by the way, let's go ahead and fill this out. So this would be 0.6 here, and this would be 1.6 here. So this number comes over here. This number comes over here. Okay, so what we're going to do is we got to make a ratio. So for hydrogen, it's going to be 1.6 over 0.6. And if you do the math, that's going to be 2.67. For the carbon, it's going to be 0.6 over 0.6, and that's going to equal 1. So now what you have to do is you have to multiply that by 2 to see if you get a whole number, and the answer is you won't. Then you multiply by 3 to see if you get a whole number, and you will. You're going to get 8. Okay, again, if it's 7.99, 8.01, that's fine. That's 8. Then you multiply this by 3. Okay, so that means it's going to be, your empirical formula is going to be C3H8. Okay, then you're going to have to convert to figure out the molar mass of this, and you need to show your work on that. Okay, you can't just write down the number I write down. It's going to equal 44.11 grams per mole. Okay, that's the empirical molar mass. Empirical empirical molar mass. Then you make a ratio, you find your N. N is the ratio of the molar mass of the actual substance, and I give that to you right here. Okay, and so that's going to be 44.11. Okay, and the empirical molar mass over the empirical molar mass, and we just calculated that's 44.11. Okay, and that's going to equal 1. So that's your multiplication factor. So you multiply that by the actual empirical formula. So 1 times C3 is C3, 1 times H8 is H8. In other words, you're multiplying either of those subscripts, and you're going to get the final molecular formula of C3H8. You need to write all this out or you don't get credit. Okay, this is not a copying exercise. So go ahead and do that calculation. Okay, number 24 is actually identical to number 22, not the numbers, but the type of problem it is. So I'm going to let you do this one. I'm going to just write the same method as number 22. And you need to do that one on your own. Okay? All right, it's simply grams to moles, make the ratio. If it's whole numbers, you're done. That's the empirical formula. If not, you got to multiply by a whole number to get the actual empirical formula. Now, again, I use the word whole number and integer interchangeably. They mean the same thing. Okay, it's a number without any decimals or fractions. Okay, all right. Now we're going to do one that deals with mass percent. Okay, and assuming, so you have to write this assumption. So you're assuming a 100 gram sample of this aluminum and this chlorine. Okay, if you do that, then for the aluminum, 20.2% turns into 20.2 grams. Okay, and for the chlorine, okay, so this is what you have: grams of that, grams of that. So now you go to the periodic table, and for aluminum, I'll do the calculation down here. It's going to be 20 grams, 20.2 grams, times the molar mass of aluminum, and that is going to be 26.98 per mole. So 1 mole. Okay, it's going to give you 0.75 moles of Al. Come up here, do the same thing for the chlorine. Come over to the periodic table, and if you look at that, it's right there. It's 35.45. And we get 2.25 moles of Cl. Okay, now you make a ratio out of these two. Smallest one on the bottom, these two right here, this and this. And you get 3. And for the smaller of the two, so this is for chlorine, and for the smaller of the two, aluminum, it's just over itself. 7.5 over 0.75 equals 1. Okay, so this one is for aluminum. This one's for chlorine right here. Okay, so it's simply Al1Cl3. Okay, and it's simply, the answer is going to be Al1, you don't have to write the 1, Cl3. Okay, and that's the empirical formula there. All right, we're now moving on to this one, and this one is the one that's a little more involved because it's a lab scenario. So a student is assigned the task of determining the moles of water in 1 mole of MgCl2 times NH2O. So this is called the empirical formula of a hydrate. Hydrate means it has a water molecules attached. Okay, so the student collects the data below. Okay, so let's look at what's going on. So first they mass the empty container, which they're going to be doing the experiment. There it is. Then they get the initial mass of the sample, the container and the sample. That's this entire thing right here, including the water molecules, okay? And that's what they get there, all right? And then next they do a first heating, and some of the water has evaporated off. MgCl2 does not evaporate. It stays in the container. Then they do a second heating, and some more of the water has evaporated off because this number is less than this one. And then they do the third heating, and you see that these last two numbers are essentially the same. 1/1000th off, that's effectively the same. So that's how they know all of the water has been evaporated, okay? So let's go ahead and number these lines. Here's 1. This one is 2, 3, 4, and 5, so we can reference them, okay? Well, we're not really interested in these intermediate numbers for the amount of water that's been removed. Some of it has, but some of it hasn't. So we can pretty much put a line through this. We don't need this number here. And we can put a line through this. We don't need this number here. So the only three we're interested in is 1, 2, and 5, okay? So what you need to do is find out how many moles of MgCl you have and how many moles of H2O, because empirical formulas always have to use moles, not grams, okay? So how do we figure that out? Well, if we take the mass of the sample container after the third heating, that means all the water, you can write this down as a note, all H2O is gone, and you have only MgCl2. Okay, so what we need to do then is we need to take that's the mass of the sample container after the third heating and the mass of the sample in the container. So this is really sample minus H2O. So if we subtract these two numbers, so subtract number 2 minus line 5, you'll get the mass of the water, because this is MgCl and H2O, this is only MgCl, so that means the difference between those two is how much the H2O weighed, okay? So we're going to do that. Okay, and that tells you that you end up with 1.848 grams of just water. That's what got evaporated away, okay? So now we know the grams of water, we can figure out the moles. Let's first figure out the grams of MgCl2. Okay, so here is the mass of the sample and the container, and again, this is MgCl2 only. Okay, this line right here. Okay, so if you got MgCl2 only and the container, and you subtract the weight of the empty container, that will give you the mass of the MgCl2. So let's do that down here. So it's line 5 minus line 1. Okay, so this minus this will give us the mass of just the MgCl2, so we'll go ahead and do that. Okay, and that gives us 1.63 grams of MgCl2. Okay, so we know this number, grams of this, grams of this. Now we need to figure out how many moles that is. All right, so the molar mass for H2O we know is 18.02. We use that all the time. And here's the molar mass for the MgCl. So we'll go ahead and do the water first. Okay, and that gives us 0.10, rounded to two places after the decimal, moles of H2O. Now we come down and do it for MgCl2. And we see the molar mass up here is right up here, okay, given to us 95.21. Okay, and that gives us 0.017 moles of MgCl2. Okay, so there's our two numbers of moles. I'm going to come up here above where I have a little more room, and I'm going to make a ratio. Okay, the smaller number is 0.017 on the bottom. Okay, and if you do the division on that, you get 5.88, and we're going to call that close enough to 6. And for MgCl2, 0.17 over itself, smaller on the bottom, smaller at the top. Okay, equals 1. So that's going to give us a final empirical formula of the hydrate of MgCl2 times 6 H2O. You have 6 water molecules attached to that, okay? And that's the final answer. A lot of steps, but it's like anything else in this class. If you practice it and practice it, some of you may only need to practice it twice, some of you may need to practice it 6 times, okay? It's what you need to do to understand it. You can understand it, okay? All right. Okay, and one final point about this problem. If I carried this number, 0.10, out one more decimal place, 0.103, it would have come out up here a lot closer to 6. Instead of 5, you would have gotten almost exactly 6, okay? All right, so we'll move on to the next problem.